Intermediate vector bosons, 1983. In his original theory of beta decay, 1933, Fermi treated the process as a contact interaction occurring at a single point and therefore requiring no mediating particle. As it happens, the weak force which is responsible for beta decay is of extremely short range, so that Fermi's model was not far from the truth and yields excellent approximate results at low energies. However, it was widely recognized that this approach was bound to fail at high energies and would eventually have to be supplanted with a theory in which the interaction was mediated by the exchange of some particle. The mediator came to be known by the prosaic name intermediate vector boson. The challenge for theorists was to predict the properties of the intermediate vector boson and for experimentalists to produce one in the laboratory. You may recall that Yukawa, faced with the analogous problem for the strong force, was able to estimate the mass of the pion in terms of the range of the force, which he took to be roughly the same as the size of a nucleus. But we have no corresponding way to measure the range of the weak force. There are no weak bound states whose size would inform us the weak force is simply too feeble to bind particles together. For many years, predictions of the intermediate vector boson mass were little more than educated guesses, the education coming largely from the failure of experiments at progressively higher energies to detect the particle. By 1962, it was known that the mass had to be at least half the proton mass. 10 years later, the experimental lower limit had grown to 2.5 proton masses. But it was not until the emergence of the electroweak theory of Glashow, Winberg and Salom that a really firm prediction of the mass was possible. In this theory, there are in fact three intermediate vector bosons, two of them charged W plus minus and one neutral Z. Their masses were calculated to be MW equal 82 plus minus 2 gigaelectron volt per c square, MZ equal 92 plus minus 2 gigaelectron volt per c square. In the late 70s, CERN began construction of a proton-antiproton collider designed specifically to produce these extremely heavy particles. Bear in mind that the mass of the proton is 0.94 gigaelectron volt per c square, so we are talking about something nearly 100 times as heavy. In January 1983, the discovery of the W at 81 plus minus 5 gigaelectron volt per c square was reported by Carlo Rubia's group, and 5 months later the same team announced discovery of the Z at 95 plus minus 3 gigaelectron volt per c square. These experiments represent an extraordinary technical triumph, and they were of fundamental importance in confirming a crucial aspect of the Standard Model, to which the physics community was by that time heavily committed and for which a Nobel Prize had already been awarded. Unlike the strange particles or the psi, however, the intermediate vector bosons were long awaited and universally expected, so the general reaction was a sigh of relief, not shock or surprise.